Okay, in this experiment, you're designed to create a 1-second oscillator. So what we attempt to do in this experiment is to calculate what weight is required on the system. I'm going to do it by hand in a minute. You can see at the moment it's oscillating a lot faster than 1 second because we haven't got the correct weight onto the system. As we add more weight and we start the oscillation again, you can see it's oscillating slower, okay, but still not at the correct rate. Now the idea isn't to just add weight to the system until you happen to actually come across the correct frequency of oscillation of 1 second. The idea is you to, by experimentation and results, calculate the mass required in this system to create a 1-second oscillator. So let's go through the procedure. So first of all, our references. Now it says in the experiment sheet that rather than just having the springs on their own like so and having this as your zero reference, it's not ideal because it's best to have some pre-tension on the springs. So what we do is we hang the hanger on its own and we class that as a zero weight. Okay. You have a reference then measured off with a ruler. Okay, this is a scale here going from 0 down to 1 meter down to the floor. And we go across where the bottom of the weight is. It's oscillating a little bit, but let's settle. We class that as a 0 and 1. Now it's showing 26 centimeters, but you've got to realize that is applicable to the 0 reference. Now, you add weight to the system. So in the first column, 0 weight means 0 force. The displacement would be 0. We add a mass of 0.5 kilograms. Sorry, 0.05 kilograms, sorry, which is 50 grams. So we add 50 gram weight to the system. You can see it's displaced. We retake our displacement measurement. Okay, and I'll read off here. Now, I'm not doing exact reading, I'm going to look roughly for this video purposes. And that's gone to 31 centimeters approximately. So we've got a displacement from 26 to 31, which is 5. So we keep on doing that for the extra weights. The next weight is 100 grams. So we can actually add another 50 or add this other 100 on. I'm just going to add another 50 on the moment. And then you get another displacement and you re-measure that displacement down on your ruler. Okay, so if things are correct, it's a linear relationship, so that displacement must be linear to the weight we're adding to the system. So as you progress through, you go 50 grams, 100 grams, 150, 200 grams, 250 grams. So you'll have 5 readings plus your initial 0 value reading. So we have force. Now force is in newtons. Obviously you should know that force is the weight or mass times gravity. Okay, we can use a rounded value for gravity. It doesn't matter what, it doesn't have to be exact. It doesn't have to be 9. It could be 9.8, 9.812. Okay, somewhere around that mark. It's a linear relationship. We're not worried exactly what gravity is because it will give a linear relationship on the graph paper. So we have the values. So Hooke's law states that force is equal to a constant times displacement. So what do we do? The first thing you must do is actually plot a graph. Now that graph obviously is going to be your force against your displacement. Now I'm not going to say which axis they're on, it's up to you to decide which axis should be on which. But applying the formula, once you've got your graph, now the graph will be a straight line. It will intersect at 0, 0 because our first measurement is force is 0 and displacement 0. And you'll have for each weight or force, you'll have a displacement measurement and you will get a straight line on the graph. Now, since force is equal to a constant times displacement, the slope of the graph will give you the value of k. That's what we're after. That's what we want to extract from the graph. Once you've got your value of k, we can go on to the second part of the experiment. So, second part, you'll see an equation, and the equation is t, being time, is equal to 2 pi and the square root of big M plus 3m divided by k. Now, I'll tell you what the things stand for. T is the time. Now, as we said before, we're trying to create a 1 second oscillator. Big M is the mass of your weights you're adding onto the system. Small m, that's why it's 3m, is the mass of the springs. So we tend to weigh all the 3 springs together. They don't weigh much, but they still add to the whole mass of the oscillating system. Now rearrange the formula to create m the subject of the formula, because that's the unknown. What is the mass for the 1 second oscillator? We know T is 1 second. We know K, the slope of the graph. Once we've got a value for mass, we load up that system with that mass. Now we've already included the mass of the springs. Now at this point, it's very relevant. We do include the weight of the hanger. So the weight of the hanger on its own is 50 grams. So I've got 50 at the moment. The weight of the hanger plus 250. So I've got 150 grams on there at the moment. You weight up the system, whatever calculation you get from M being the weight. So we have small weights here. We've got some 10 grams, some 2 grams and 1 gram. So you can get to the nearest gram with all these weights here. Okay, let's assume the value is 250. So I'm going to actually put on 250 now. So remember we've got the weight of the hanger, that's 50, plus another 100, it's 150, plus 2 more 50s, 250. So let's assume that's your M you calculated. Now, what we do for the measurements of this oscillator, we have a stopwatch, and you'll see on the table, we rather than try and time one oscillation, we time several oscillations. Okay, so the first one we run it for 10 oscillations. Now, I'm just going to get this oscillating. Now, it will oscillate at the same rate. People say it's slowing down. The period of oscillation is slowing down. That's not true. What's decaying is the displacement. The period of each oscillation is constant. Okay, so now where do we measure when we start our stopwatch? Do we have to measure the top, the bottom, or the middle? Now, because due to dampening, it's not actually going as far as it went before. We need to measure somewhere in the middle. So you have with my fingers as the reference point. So we start our timing and we start our counting. Remember to start the count from 0, not 1. So we start a timer, counting, and when we get to 10, we stop the stopwatch. Now we repeat that in the table for 20 oscillations. The concept here is the more oscillations you actually count and time, the more accurate your result will be. Now, once we've got that, it's quite straightforward to get enough time for 1 oscillations. If we had a perfect system, it should take 10 seconds to do 10 oscillations. Divide one by the other, we get our 1 second oscillator. You, in theory, will probably get some error, and that's where we talk about the measured minus predicted value or the predicted value. Now, this could be a positive or negative error, depending if your timing is short with the 10 oscillations or it exceeds the 10 seconds for 10 oscillations. I think that's it. That concludes the experiment.